Hello everyone. In today's lecture we are going to talk about a very important notion that is associated with poles and zeros of the transfer function, and therefore we are starting with saying transfer function poles and zeros. Poles and zeros. We already concluded that if we have a state space representation x dot equal a of x plus p u y equal c of x, transfer function of this state space representation by applying Laplace transform and assuming initial conditions being 0, which usually we can take since the initial conditions are associated with the transient behavior of the plant. So this is the transient behavior in the plant until plant gets into some steady state. This is the time, and this is, let's say, the x of t. We obtain that y of s is c s I minus 1 b u of s. So we call this above expression as g of s, transfer function u of s. So this g of s is our transfer function. This transfer function, so we just write transfer function. Transfer function, in this case, it can be written also for a seesaw system, single input, single output, as division of two polynomials, n of s and p of s. And this is the moment where the notions of the poles and zeros of the transfer functions are coming into the play. Namely, n of s polynomial provides the zeros of the transfer function because n of s equals 0 solutions are zeros of the transfer function. Zeros of transfer function or zeros of g of s. Okay, so this is if root of this polynomial n of s is solution of this polynomial, or 0 of this polynomial is also 0 of the transfer function. In other words, if n of s is s cube plus a2 s square plus a1 s plus a0, and we equate this with 0, we will get the following. We will get the following, that the n of s has 3 roots. In other words, n of s can be factored as s plus s1, s plus s2, and s plus s3 equals 0, where s1, s2, and s3 our solutions to this equation are roots of n of s. Okay. In other words, zeros of the n of s are zeros also of the transfer function. What is the other notion that we have? We have the zeros of the p of s polynomial, and p of s polynomial can be given as s of n plus a of n minus 1 s of n plus a n minus 1 plus a n minus 2 s n minus 2 plus a 1 of s plus a 0. And the zeros of p of s are poles of transfer function, or poles of g of s. Okay, this is very important notion because the zeros of the transfer function, zeros of p of s, the zeros of p of s are poles of the transfer function. It is important because poles determine the response. System response. Namely, if we have the transfer function of the system, so I'm saying y of s is equal g of s multiplies u of s, and if u of s is Dirac function, in other words, entire plant is sitting at some steady state 0 values. If we apply the Dirac function input, the time, and we apply the Dirac function here, this is the Dirac function, the output of the plant, and we assume the plant is stable, is just going to be nothing but a response of the system to this Dirac function excitation. Okay, and it will be determined by the evolution obtained by factoring the poles. Let us demonstrate this. So y of s is g of s multiplies 1, and that's n of s, p of s, and since the P of S can be factored in S plus S1 bar S plus S2 hat plus S plus S, and we see that this can be expressed as A1 S plus S1 plus A2 S plus S2 plus A n S plus S n. Okay, this leads to the A1 e to the minus S1 of t after we apply inverse Laplace, A2 e to the minus S at 2 of t, and this last one is just going to be A and e to the minus S bar n of t. Okay, so you see that the time behavior is completely determined by the poles of the transfer function. We also see that the stability of the system is associated with positive poles. So if the poles are placed in the coordinate system where this is real axis, this is imaginary, anywhere in the 8HP, those are unstable poles. Unstable poles. While here we have a stable poles. So let's say this is the distribution of the poles of the stable poles. And why stable and unstable? Because positive poles means that this time evolution of these terms is going to diverge as time goes to infinity. This is all for today, and we will continue by explaining what happens if the signal that is applied to the plant contains pole or zero of the transfer function.